You ever look at a tiny computer chip and just wonder how it does what it does? I mean, billions of calculations in a split second. It seems like magic, right? Well, the answer is kind of complex, but it's also beautifully simple, and it all starts with the smallest things you can possibly imagine. So, what we're going to do here is build the most fundamental piece of all modern electronics, right from scratch. This is our roadmap. We'll start with the atomic foundation, look at the materials that conduct electricity, get into a game-changing process called doping, see what a p-n junction is, and finally, figure out how to build a one-way street for electricity. Let's get into it. All right, first up, the atomic foundation. You know, to really get how a computer thinks, you have to start with what it's made of. And I mean really start, like all the way down at the atomic level. So what's an atom? It's basically the smallest possible piece of an element that's still, well, that element. Everything around us, everything you can see and touch, it's all just made of these tiny, tiny building blocks. And inside each atom, you've got three main players. Right in the middle, in the nucleus, you've got your protons, which are positive, and neutrons, which have no charge. Then, zipping around the outside, you have the negatively charged electrons. So you have this positive core and this cloud of negative electrons spinning around it. Simple enough, right? But here's the key. That little negative particle, the electron, that's our superstar. It's the particle that does all the heavy lifting in electronics. Actually, to be even more specific, we really only care about the electrons on the very edge, in the outermost shell. We call these valence electrons. And you can think of them as the atom's social butterflies. They're the ones that get out there, mingle, and form connections with other atoms. They are the real heroes of this story. Which brings us to our star player, silicon. So why silicon? Well, look at this. It has exactly 4 of those valence electrons. Not one, like you'd find in a great conductor like copper, but 4. And that number, 4, is the magic number. It's what makes silicon so special. It makes it a semiconductor. Okay, moving on. Let's see how these valence electrons completely change how a material behaves, specifically its ability to conduct electricity. You see, for an electron to move around and create a current, it needs a little boost of energy. It has to jump from its comfortable home, the valence band, up to a higher energy level called the conduction band. And that gap between them? We call that the band gap. And this is so cool because it shows you everything you need to know. The entire difference between materials comes down to the size of that band gap. Is it easy for an electron to make that jump, or is it next to impossible? Right. So in an insulator like rubber, the gap is massive. The electrons are totally stuck. In a conductor like copper, there's no gap at all. The bands just overlap so electrons can wander around freely. But then you have semiconductors like our friend silicon. They're the Goldilocks material. The band gap is small, it's manageable, we can persuade those electrons to jump, and that means we can control them. So, how do we persuade them? How do we actually get those electrons to do what we want? Well, this is where it gets really clever. We kind of cheat, using a brilliant process called doping. Doping is this amazing technique where we intentionally sneak a tiny number of impurity atoms into our perfectly pure silicon crystal. It's like adding one special player to a sports team that completely changes the way they play the game. And there are 2 main ways to do this. On the one hand, if we add an impurity that has 5 valence electrons, like antimony, we end up with an extra free electron just hanging around. We call this N-type for negative. But if we add an impurity with only 3 valence electrons, like boron, we create a deficit, an empty spot where an electron should be. We call that spot a hole, and the material is now P-type for positive. So what have we done? This is the key takeaway. We've just created 2 brand new custom materials. We've got N-type silicone with a bunch of extra electrons, and P-type silicone with a bunch of extra holes that are just begging to be filled. Now, for the real magic. What happens if we take a piece of our N-type material and a piece of our P-type material and just stick them together? Let's look at that boundary, the p-n junction. The second they touch, something totally natural happens. All those free-roaming electrons on the N side look over, see all those empty holes on the P side, and they just start rushing across the junction to fill them. It's just diffusion. But this can't go on forever. As the electrons cross over, they leave behind positively charged atoms on the N side and create negatively charged atoms on the P side. This creates a barrier of static charge right at the junction. We call it the depletion region. and this region acts like a wall, stopping any more electrons from getting across. If you think about it in terms of energy, this depletion region creates a kind of energy hill. The rest of the electrons on the N side just don't have enough juice to climb that hill and get to the other side. So everything settles down, the flow stops, and we reach a nice equilibrium. Okay, so we've built this structure. It has this natural barrier built right into it. Now for the payoff. How do we turn this thing into a dynamic switch that we can actually control? It's simple. We use an external voltage. If we apply a voltage in a way that pushes the electrons and holes towards the junction, we call this forward bias, it shrinks that barrier and boom, current flows right through. But if we flip the voltage the other way, called reverse bias, it pulls everything away from the junction, makes the barrier even wider, and blocks the current completely. What we've made here is basically a perfect electronic valve. It lets electricity flow freely in one direction, but slams the door shut if it tries to go the other way. It really is a one-way street for current. And this graph is the proof. This is the signature current voltage curve for our p-n junction, which, by the way, we now call a diode. See? In one direction, almost no current gets through, nothing. But in the other direction, once we give it a tiny push, about 0.7 volts for silicon, the floodgates open and current flows. It's a switch. It's either on or it's off. And really, that's it. This unbelievably simple idea, this electronic one-way gate, is the fundamental building block of our entire digital world. It's the basis for diodes, for the transistors that power our phones and computers, every single microchip. So it kind of leaves you with a big question, doesn't it? Now that we know how this simple little switch works, what are we going to build with it next?